Thanks, Joe. I've kind of changed the title on you, Joe. Of course, I'm talking about large-scale features in turbulent pipe and channel flows. I'm pretty much following on from what Nick was talking about. He's a bit of a hard act to follow, so I'll try and do this justice. We've been looking recently at the large-scale motions, but as a comparison between channels, pipes, and boundary layers, something Javier has already spoken about this week. Okay, so the motivation is basically what Nick has been doing a few years before I started. Also, Ron Adrian's group has been looking at these large-scale motions in pipes for more than 10 years, and Javier Jimenez's DNS has also helped us understand large-scale motions in channel flows. But I thought we'd do it experimentally. We put these rakes of hot wires in the channel and pipe. I won't go into any details about the experiments. You can ask me about those later. Basically, what we see is this is a streamwise, spanwise slice of turbulent of velocity fluctuation, streamwise velocity fluctuation. The blue is low speed and the red is high speed. Taylor's hypothesis, of course, we're using these are hot wire measurements, so you have to be careful what we're looking at. But we see these long features. Okay. As we move away from the wall in the channel, we see things get a bit wider. We still see the structure. We still see the long features, even quite a long way from the wall, out to halfway to the center line. And things seem to get wider as we go out. For the pipe case, I'm showing you a 2D version here. See a similar kind of thing, but it's a little more interesting. If I swing this around, and I'm showing you a 2D projection. That's not the real coordinate system. So if I wrap that up, this isn't just a pretty picture. I hope it is pretty to you. But we see these low-speed features again. But now Nick talked about these things meandering for a channel and a boundary layer. Meandering for a pipe means rotating about the pipe, which I think is kind of nice. And you might say, well, Taylor's hypothesis, you've got to be careful. I see these things rotating over just a few delta from one side of a pipe to another in various visualizations. So I think it really happens. But anyway, the point I want to make with all these is in a pipe, a channel, and a boundary layer, three completely different geometries and facilities, we see the same kind of features, which are long meandering things. So say what you like about Taylor's hypothesis, it looks the same for all these three geometries, qualitatively at least. But we need to go a bit further than that. I can show you these all day. They're just subjective. They're just what I want you to see. I can look at statistics and show that things are a bit more understood. So here I'm plotting the 2-point correlation of streamwise velocity in the spanwise direction. And what you see is these two negative troughs, and of course the positive in the middle. That's indicative of high speed, low speed, high speed. Okay, so it shows you that what we see in the visualizations is statistically there. What's really interesting about this plot is I've got a channel, a pipe, and a boundary layer. The channel and pipe are almost the same in the log region, at the edge of the log region, but the boundary layer is clearly more narrow. At least it's different. And it's more narrow, in fact. And as we go out from the wall, this thing's going to respond. This is just one example. As we go out from the wall, things get wider. We saw this in the visualization, but statistically it happens. And if I pick a width scale, in this case I've just picked the red arrow, the distance between the correlations at some point. Doesn't matter what it is for now. You see that as we go away from the wall, statistically things get wider. And it's a kind of linear growth. It grows all the way to the center line of the channel, which I think is quite interesting. But when I plot the boundary layer on top of there, it's a different scale. Even in the log region, I'll show all the data I can find in the literature. Even in the log region, there's DNS there. Even in the log region for the pipe and channel, we've got a factor of about 1.7 bigger than the wider, at least, than the boundary layer. And as you go out from the wall, you get much wider things in the channel than the boundary layer. Okay, so at this point I make the conclusion, what I just said. Pipe and channel structures are on average wider, even in the log region. And that was a bit of a surprise to us. Okay, so after we finished that work, we decided to do a more detailed comparison, and Nick Hutchins and I have been working on that for the last 9 months, I guess. And at Melbourne, we're lucky enough to have a pipe, channel, and boundary layer facility. They've all been well tested and can get to reasonably high Reynolds numbers. I guess I should call them moderate. But we're able to match the conditions, we're able to match the hot wire length, and we think we've made some very careful measurements in all three facilities to make a nice comparison. So here I look at the mean velocity in inner scaling. Some of you may have seen this. You may not have seen it at the same Reynolds number like we've got here. The boundary layer, of course, has the highest wake, the pipe next, and the channel is the closest to the log law throughout the layer. And they all collapse pretty well in the log region. But actually today I'm going to talk more about, I'm going to plot everything in this scaling, so outer scaling with a linear axis, because I'm interested in the outer flow. So everything I'm going to compare from now on is in the outer flow. And I think, I don't know, if I step back from there and have a look, those three things look pretty similar. For the difference in geometry that we have, it's not a huge difference, but anyway. If I look at the turbulence intensity, and I'm going to block out everything near the wall. I'm only interested in far from the wall. And things collapse pretty well. Javier's already shown this, that the channel and the boundary layer collapse in terms of turbulence intensity, streamwise turbulence intensity. We see the same thing here. And in fact, for most of the flow, until about halfway up to the half of delta or halfway up the channel or pipe, we have good collapse. And then the turbulent core starts to kick in. Okay. And what we really want to look at is the streamwise energy spectra. Nick's shown that we can understand a lot about the flow by looking at these plots. And I'm going to do the same thing that Nick did, plot this bread slice plot. So I'm stacking up energy spectra in the top, and I'm plotting the mean velocity and the turbulence intensity in the bottom. And Ivan also showed these plots, but the different thing that I'm doing is I'm plotting on a linear axis. Wall distance is a linear axis, because I'm interested in the outer flow. And we start at a point in the log region, the beginning of the log region. You see, you can't see that well. I'll blow it up in a minute, but everything's very close. And as we go out, I get to the point where Nick will say the superstructures peak. And if I blow that up, I'll look at the back. That's the spectra. Things kind of look the same. If I take an even closer look, I have the superstructure peak here, which Nick spoke about. It seems to be about the same scale for pipes, channels, and boundary layers. So I would say that those are kind of similar. I mean, at least the energy is in the same scales. But there is a difference, of course. We have less energy for the pipe and channel at smaller scales and more for the higher scales. I'll repeat that the turbulence intensity, or if you like, the energy under all these curves is more or less the same. The area under all these curves is more or less the same. And I'll label that point throughout the talk. So if I keep moving out, I get to the edge close to the edge of the log region, but I'm still in the log region. You see there's bigger differences now if I zoom in. What you see is the superstructures in the boundary layer have kind of saturated, I guess. They're not getting any longer as we go away from the wall. The energy still drops off straight after that superstructure peak. Whereas the pipe and channel are clearly moving out. Things are getting longer as we get away from the wall. And this is what Ron Adrian's group calls the very large scale motion, which I'll show you a picture of in a minute. But clearly now there's a difference. There's a structural difference between the two flows in the log region. And again, less energy in the smaller scales for the pipe and more energy in the larger scales for the pipe and channel. And I guess still amazingly, the pipe and channel are pretty much exactly the same. Okay, so still turbulence intensity, mean velocity are very similar. We move out to about a third of the boundary layer, a third of the way up the pipe or channel. I think things are starting to get very interesting now. We have this large scale motion at peak in the boundary layer, which is about 3 delta long. But in the pipe, you see the emergence of two different peaks now. We have one that's the same as the boundary layer, the large scale motion peak, and one at a very large scale motion, which is much longer. And at this point, I should remind you what Kim and Adrian's model was to explain. They've already seen this spectra. I'm not showing anything new, just the comparison is new, I guess. They've already explained this behavior. So they say that there's these vortex packets, which many people have already seen. And if you've forgotten, the idea is that it's exactly what Tim was saying the other day. We have the packets of large-scale motions of length about 3 delta. Doesn't matter what you think is in that structure. It's 3 delta long. And it's got to be there because it's in the energy spectrum. And the VLSM, wake up, is just the alignment of those large-scale motions. So the alignment of these 3 delta packets. I think that's pretty well established. I think Tim showed it very nicely yesterday. Okay, so I want to mention a little bit about the mechanism. Well, not so much what it is, but what's involved. So I've been saying all along the energy at this point is still the same for all three flows. The area under the boundary layer pipe and channel is the same. So if you consider the basic building block to be these 3 delta long structures, what we're really saying is that for the pipe and channel, energy is taken away from that large scale motion and it's redistributed to this very large scale motion. But there doesn't seem to be any energy gain or loss, which is kind of perplexing. You would think that if there is a mechanism to pull these things into alignment, you'd think there'd be some energy gain or loss associated with that. So the only point I really want to make about this is whatever pulls these packets into line doesn't seem to be associated with any energy gain or loss, which I think you have to keep that in mind when you're looking for a mechanism. Okay, so as we keep going out, I'm going to show you one more point. All I want to say here, we're about halfway up the channel or pipe now. The large scale motion is still about the same length, about 3 delta, and the very large scale motion is still growing. It's still kicking out there and it still exists up to about 0.5 delta. We're a long way from the wall now. And we have lengths of over 20 delta. And they're clearly there in the energy spectrum. Okay, so I'll just finish that off. The last one, of course, there's no energy in the boundary layer. We're at the edge of the layer, but there's still something in the pipe and channel. I can make this a little more clear by showing what Nick showed, and I guess you've already seen this. So I take that energy map, or the bread slice plot if you like. I plot it with contours of kx phi u, or pre-multiplied pre-multiplied spectral density. Rotate that. And we're looking down on this map. Nick's already shown it, so I won't go into too much detail. What he showed looks something like this, and he showed you where the superstructures, thing's not responsive. He showed you where the superstructures exist. If I look back in linear scaling, that's where they are. I like this scale because we're looking at the outer flow, and this really shows you that the only thing, the biggest thing in the outer flow is the superstructures. It's the only feature you can see there. And also we see this 3 delta long, or I guess this 3 delta peak kind of persists all the way out through the flow and doesn't really move around much. If I go to the pipe and just flick between those two for a second, first of all, for the pipe case, I show you where the superstructure peak was for the boundary layer. For the pipe, it seems to be at longer lengths and a little further from the wall. But we still have this 3 delta long structure, which I find kind of amazing. I'm amazed that there's anything similar right out here. Anything similar between pipes, channels, and boundary layers. But that length scale is about the same. But the big difference, of course, is this very large scale motion. And the interesting thing about that is how fast it grows. As you come out of the log region, it grows very fast to very long wavelengths and seems to continue growing. And the other interesting thing, I guess, if I flick between these two, pipe and channel, the only thing that's really changed very slightly is contour levels. So the pipe and the channel are pretty much the same. They're the same structure, at least, all the way through. And just, do I have a bit of time? Okay. So I just want to make one point about the differences in geometry. If I look at those three, as I've said all along, I'm amazed that there's any similarities in the outer flow. Look how different those are. I should say they're all about the same Reynolds number. There's a couple of LES computations there. But the geometries are clearly different. And I think it's really amazing that the pipe and channel are so similar, given these geometries. But one interesting point, I think, in terms of thinking of things in wall-up terms, if I look at the channel, this is Javier's DNS data. I'm showing you a correlation map. I'm correlating the shear stress at the wall, so an event right at the wall, the bottom wall, and I'm correlating the velocity throughout the field with that. And what you see is this positive, negative kind of correlation that's indicative of the hairpin or streamwise vortex type structure. But what is almost is strong, that correlation, okay, the correlation is weak, but it's there. And there's this anti-correlation right across the channel. And I don't know if this is significant, but I think it is. If I look at that, this is what I'm talking about. Big low-speed feature at the bottom, big high-speed feature at the top. And I guess this has to happen. I mean, it's probably not surprising when you see me circle it like this. And so I think that's got to have implications. I mean, something huge happening on the wall is modulating what's happening on the top. I think this is important. So just to conclude, I think there's qualitative similarities, which I think is amazing given the different geometries. There are important structural differences which we have to keep in mind, mostly that there's very large scale motions that I think are different to superstructures between pipes and channels and boundary layers. Thank you.
Quick question. There's something that concerns me or confuses me, whichever is what I say. When we start talking about comparing scale locations or actual scale values between a boundary layer and a pipe or a channel, you know, the boundary layer outer scale is somewhat arbitrary, right? So, I mean, is there? It seems like if you don't solve that problem, all you can talk about is relative locations.
Yeah, sure.
Right? So is
Yeah.
that
Okay.
consistent? Yeah.
That's fair enough. I mean, but how much would you consider the boundary layer length scale to change by, I guess, is a question. If you use all the different, I guess, usually accepted things like delta 99 or delta cols, you got about 20 or 30% difference. If I was to adjust for those, you're still in the same ballpark.
That's what I was just wondering. If I shifted two of your spectra, the boundary layers.
Yeah, but by 30% on a log scale.
Would you be interpreting it a little bit differently? That's what I'm wondering.
I guess one thing I haven't looked at is whether you're actually measuring at two different positions from the wall. Mm-hmm. In terms of wavelength, I think it's nothing, because we're plotting on a log scale, 30%, it's still going to be in the same ballpark. But yeah, maybe different distances from the wall might be an issue. But we sort of played around with this, played around with different deltas, and I think we're pretty happy with the comparison that we have. But it's a good point.
John?
Yesterday, I was very surprised to learn that there's such a big difference between pipe and channel. Now today, you're saying pipe and channel the same, while the boundary layers are different, but that's fine. Is there any possibility that the pressure gradient, in fact, playing a role of some difference between boundary layer and channel? And also, perhaps comparing the same RE tau may not be the right number to use.
Yeah. Well, Peter mentioned that. I think that's quite possible.
And also, it would be interesting you do some really that's slightly favorable pressure gradient, however small that is, whether or not making some differences here.
Also, these structures are so long that it's going to realize that the boundary layer is non-parallel. So the spacing is going to change. So the alignment is not going to be as long in a boundary layer as in a pipe or channel.
Yeah, that's what we see. Yeah.
So what is the spacing for the channel flow?
The channel flow.
Can you show the last correlation picture?
This?
Here.
Yeah,
So
I'll take a look. I mean, it's deep, it's going like this. So it depends where you pick, but I don't know, a couple of channel heights.
well, that is wall normal.
Yeah, it's deviating. Things get wider as you go out from the wall. So the spacing is changing.
So at the wall, what is it? H?
Yeah, H is the channel half height.
Huh?
H is the channel half. Oh, sorry. So we're using the same notation that Nick used. Y is span-wise.
Yes. So what is the span-wise scaling of the structure at the wall? 100 wall units as usual.
Oh yeah, sure.
So
but you can't see the wall here. I'm plotting on a linear scale. Is that what you're asking? Yeah, we'll go down to 100 wall units at the wall. Yeah.
Right. So you would say something like from -1 to 1, it's 2, yeah, and a bit.
Yeah, sure. It's Y.
And
Whether the scaling should be different to pipes for pipes, channels, and boundary
the
layers.
middle of the channel. It's
In the middle of
about
the channel.
very difficult to say. Well,
Yeah,
you
there's
have
almost no correlation.
to make a minimum of the span-wise correlation, right? It's 2 point.
2 points.
Okay, well, with that, let's